All right, week 3, we're going to be talking about dimensional measurement techniques. This is course content of the week. And let's begin with the introduction. So let's begin with metrology. What is metrology? Metrology is the science of measurement. And engineering metrology is defined as the measurement of dimensions such as length, thickness, diameter, flatness, and profile. So engineering metrology is really important for us. Why it is really important for us? Because imagine this example, your turning machine. You have your weighs in your turning machine. And what are your weighs for? It is for to move your carriage around left and right. So your slide base has such components, such dimensions, angles, flatness, and they has to be accurate in order to machine to move uh, in order to your carriage to move along smoothly. Otherwise, it won't. So your length, your gap should be accurate. And here we have metrology in usage, so that we can have the correct dimensions. We have post-process inspection, in-process inspection. Traditionally, the post-process inspection was used. That is the mean, like you're producing your part, for example, and your inspection would be after the production is done, production is made. This is post-process inspection. But today, measurements are being made while the part is being produced on the machine, and this approach is known as in-process, online, or real-time inspection. By the way, why do we do inspection? It is for to be sure that our dimensions are correct. Okay. And now we have a term called tolerance. Tolerance are really important for us. So what is tolerance? Okay, let's say we want to produce, we want to manufacture a solid rod like this. Okay, this will be our product. And let's say I want a length of 20 millimeter in my solid. However, when the production is done, I'm going to measure it. And will it be exactly 20 millimeter like this? The answer is going to be no. It could be like 20 points millimeter maybe, but exact 20 millimeter is not possible. Such precision, such accuracy is not possible with any manufacturing process. So what I'm going to do is I'm going to say, you know what, 20 millimeter was what I want, but maybe 19.9 millimeter is also going to be okay for me. Or maybe let's say 20.1 millimeter is also okay for me. It will do my work. So that means my tolerance is plus and minus 0.1 millimeter. Why do we call it tolerance? Because you can tolerate a 0.1 millimeter variance in your length. That's why we do call it tolerance. And also, tolerance is important for us because it manages your production cost. That is the mean. If you want a smaller tolerance, your production cost going to be higher. Why? Because for to have like other accurate dimensions in your production, you would have to use better machines, and that would increase your production cost. So again, smaller tolerance, higher production cost, higher tolerance, smaller production cost. Okay, it is important to know it. And let's talk about measurement standards now. We have measurement standards so that we can talk the same language with our measurements. That is to say, like I can measure length, for example, with foot, or I can measure it in meter. Okay, so the units for length is foot, meter, feet, millimeter, and so like that. So to be able to talk the same language, we have measurement standards, and the measurement standard that we are using, the system we are using for units, we use SI, which is System International. Okay. For example, in System International, in SI units, the length is meter. The mass unit is kilogram. For length, for example, it is not feet, okay? It is meter. For mass, it is not pound, it is kilogram. Okay? Mostly, we're going to be using SI in this course and in other engineering courses. Also in manufacturing, it is highly used, SI units too. Okay, now we have numerous measuring instruments. For example, we have rulers. We have like micrometers, and those instruments has such properties called, for example, resolution, precision, accuracy, and so like that. So let's begin with resolution. Resolution is the smallest difference in the dimensions that measuring instrument can detect or distinguish. What is meant by that? Let's say you want to measure your rod again. Okay? You want to measure its length. You can measure it with a simple ruler, or you can measure it with a micrometer. So, with ruler, the smallest difference that you can detect is generally millimeter. But if you can use micrometer with your measurement, you can detect such differences of micrometer. So your resolution in micrometer is better than your ruler. That is resolution. Now let's talk about precision. Sometimes incorrectly, precision is called accuracy. So we have precision and we have accuracy, and they are not the same thing, okay? And we're going to be talking about the difference between them. So let's say we're measuring our rod again. So we have, let's say, ruler A. This is ruler A. And we have ruler B. And we are using these rulers to measure our length of our rod. And let's say I know the length of my rod is 20 millimeter for sure. Okay. Let's say I use another superior instrument and I measured it 20 millimeter. It is for sure known. Okay. So I made, let's say, 3 measurements with both rulers. Okay. And with ruler A, first I measured 20.1 millimeter. Then I measured 20.2 millimeter. Then I measured 20.3 millimeter. So the average of them are 22 millimeter, right? So precision is, I made 3 measurements, and if those 3 measurements are really close to each other, that means my precision is high. But let's say for ruler B, I made 29 millimeter. I measured 29 millimeter. Then I measured 11 millimeter. Then I measured 20 millimeter again. So what is my average? It is 20 millimeter, right? So ruler B is accurate because averages of my measurements are my correct value. It is really close to my correct value, but it is not precise. Why it is not precise? Because I made three measurements, and variations between them are really high. It is not precise. But here I made 3 measurements, and they are really close to each other, so they are precise. Ruler A is precise. But is it accurate? It is not accurate as ruler B. It is not accurate. Okay. So this is accuracy and precision. Here we have our famous dart. You're going to see this illustration a lot in your engineering education. So this dart here, is this precise? No, it is not precise because shots are really away from them. They are really apart. But the averages of them is somewhere in here. So we can say this is accurate, but not precise. Now, let's see this one. Are the shots are closer to each other? Yes. Then we can say this is precise. But is it accurate? No, because the correct value is here, but I am so much away from it, so not accurate. All right. So it is important to know. It is important to know to able to say differences between accuracy and precision. All right, geometric features of parts. So we talk about measurements we talked about measurement devices. So, but what do we measure? Here, these are the things that you can measure. You can measure length, diameter, roughness, depth, and angles and profiles. Okay? These are typical features that measured in engineering practice and in products made by the manufacturing processes. Now, okay, we have analog and digital instruments. So, as will be obvious from our description of traditional measurement equipment, accurate measurement on an analog instrument such as vernier clipper, micrometer relies on the skill of the operator, human operator, to properly interpolate and read the graduated scales. So, with analog instruments, to have accurate measurements, you should have like skillful operator. But with digital instruments, you don't need such particle skills because measurements are indicated directly. So the digital instruments can be better, a lot better than the analog instruments. And more importantly, the digital equipment can be integrated easily into other equipment, including production machinery and machinery systems for statistical process control. These are traditional measurement methods. We have rulers, calipers, micrometers. For angle measurements, we have bevel protractor. For comparative length measurements, we have dial indicators. So here, this is a simple ruler. Okay, this is the simplest and most commonly used instrument for making linear measurements. Okay, here this is a caliper. We're going to be using them in our laboratory. You're going to learn how to use them. We have a video. This is going to be your homework. Please watch it. Here, this is a vernier clipper too. The differences between them is that this one is analog. This is analog. And this is a digital one. So this is a lot easier to read, but this is not as easier to read when you compare with the other one. We have micrometers. We're gonna learn how to use them in our laboratory too. Another video, please watch it. So this is a digital one, a digital micrometer. For angle measurements, we have bevel protractor. And comparative length measurements. So this one, these devices or instruments measure the variations or deviations in the distance between two or more surfaces. Let's say you want to measure the differences, the length differences between this point and this point. You can use this comparative length measurement instruments. Here, this is a dial indicator. Please watch the video. So basically what it does is that it measures the levels between two discs. And here, modern measuring methods and instruments. Here, an electronic gauge. we use electronic signals to measure the length, height, or whatever. These are more precise and more accurate than any analog or digital measurements instruments. Here we have a video, please watch it. Laser scan micrometers. Basically, it uses laser to measure lengths. And here we have CMM. So CMMs are pretty cool machines. That is to say, like, it just works with coordinate systems. So let's say, okay, this is your CMM, and you have a monitor in CMMs. Okay, you have a PC monitor, and in this monitor you can read where your probe, this is your probe, where your probe is in space. You have your X, Y, Z coordinates of your probe. Okay. So let's say you want to measure the height level differences between this plane and this plane. So what you're going to do is that you're going to you're going to touch this surface with your probe, and you're going to have X1, Y1, and Z1. Then you're going to touch this surface, and then you're going to have your X2, Y2, and Z2. And since we want to know the height differences between them, we have Z2 and we have Z1. The height is going to be equal Z2 minus Z1. So I used the coordinate system for measuring the desired length, height, or whatever it is. This is just one application of CMM. CMMs are pretty complex, pretty accurate, pretty good machines for measuring. Hope you can work with them in your internship. These are pretty cool machines. Here CMM is illustrated. Like this one is a really wide one, a really wide CMM machine. You can measure various points with CMM. You can measure the hole diameters, the height differences, the angles, the roundness, and everything. Here we have videos, and please watch them, okay? All right, now I'm going to skip some parts, some slides. However, I want you to read them. I'm going to skip them because I want to talk about more important things here. So let's go this one. Okay, here I want to talk about like your dimensional tolerance depends on your application. That is the same. Let's say you want to make an airplane. In airplanes, your tolerance has to be low. Otherwise, airplane will not work properly. So you can spend more money to have lower tolerances if you're making an airplane. However, let's say you're making a gearbox. In gearbox, you don't need much higher, much lower tolerances. So you can have higher tolerances and spend less money because you don't need it. Okay. So dimensional tolerance is depending on your application. It depends whether you need it or not. The importance of tolerance control. So dimensional tolerances become important only when a part is to be assembled or mated with another part. Surfaces that are free and not functional do not need close tolerance control. For example, the accuracy of the holes and distances between the holes for connecting rod are far more critical than the rod's width and thickness at various locations along its length. For example, let's take this example. Look at this one. So you have your shaft and you have your hole. Okay, this is your shaft, and this is your hole, and you're looking it on sideways. So the length of your shaft is not as much as important as the diameter of your shaft. Why? Because your hole and shaft connected with each other. They are assembled with each other with their diameters. Okay. Let's say if your diameter is bigger than what it should be, then it is not going to turn. If it is really less than what it should be, then it is going to make some distortion. It's going to make some vibrations. You don't want that too. So length is not important as much as diameter here, as we said before. Dimensional tolerances become important only when a part is to be assembled or mated with another part. Surfaces that are free and not functional do not need close tolerance control. Okay? When your parts touch each other, those dimensions are important when you're controlling your tolerance. Your length is not important because they're not touching each other. Okay. Here, this is a table for dimensional tolerances. So you have your manufacturing processes, and your manufacturing processes is changes your dimensional tolerance. Let's say you're using die casting. Let's say you're using die casting, and let's say your part dimension is 100 millimeter. Okay, then your tolerance is going to be probably somewhere here. And let's say your part dimension is here, then your tolerance when you're using this manufacturing process will be probably here. Okay? This is a table for it. We have some definitions. Please read them. I'm just going to skip them. We have symbols. So you have tolerances. You have to show your tolerances in your technical drawing. This is how you represent them. How do you show them? You're gonna see a lot more about this in your technical drawing course. And we finished here now. So please read the lecture notes and please watch the videos. And see you next week.